Welcome to Hot Chips 18. Session 2, Microprocessors I.
Okay, my name is Mark Tremblay. I'm chairing this next session on microprocessors. The first speaker is from PA Semi, and his name is Tse-Yu Yeh. He's been with PA Semi for 2 years, and he's responsible for CPU architecture and chip logic verification. Prior to that, he was at Broadcom, working on SciByte, and prior to that, working on Itanium. He has a PhD from University of Michigan, and a very interesting talk.
Okay, thank you. Thank you, Mark, for the introduction. My name is Tse-Yu Yeh. I'm here to present the work we have done on the low-power, high-performance, power-efficient processor family. The first design of this processor family is called HC18-S2. It's on track for sampling in Q4 this year. It's the fruit of the untiring work by the whole team in the past 2.5 years. My talk is organized as follows. First, I will start with talking about the design paradigm for low-power, high-performance design. Then I will introduce the PA power-efficient processor family. Then I will dive into the microarchitecture details of the core. Then I will present the projected performance and power numbers. I will conclude this talk with a brief summary. The design goal of this processor core is to have IBM 970 class performance with a power consumption of less than 7 watts per core. We have this performance goal and power budget in mind from day one of the design. We make trade-offs among the complexity, performance, power, area, timing, and the project schedule. Starting from circuit and process level, we use voltage and frequency scaling in multiple power domains to achieve the optimal power consumption. At the microarchitecture and logic level, we use extensive clock gating to minimize the amount of circuit that is being clocked. We pay special attention to the size and hierarchy of the microarchitecture to make sure the amount of circuit being clocked is actually minimized. At the architecture level, we design highly integrated chip to save I/O power. We also designed in a bunch of power-saving mode for the CPU, memory controller, and PCI Express. At the verification level, we monitor and check the projected power number in every stage of the project to make sure the projected power fit within the power budget. At the software level, we develop drivers to take advantage of the power-saving modes we have designed into the chip. So for microarchitecture choices, historically, architects have been exercising the practice that performance is everything. We make things bigger, we design more parallel structures, and more speculation to gain more performance. However, all these additions cost power. So for the low power design, it's very important that we design things into the chip only when it's really needed. So if a function can be performed in sequential steps, why do them in parallel? Because with sequential steps, we can take advantage of fine-grained clock gating to save a lot of power. Another thing is if we can use a smaller structure to support most of the references, why use a large structure? Probably we should think about using a smaller structure backed up by a larger structure to achieve the same level of performance. Another important thing is any addition for performance reason ought to be evaluated for the performance and power consumptions, because the performance gain in terms of saving in execution time may not be enough to offset the additional power consumption. Last but not least, the speculation has to be done effectively. Otherwise, a lot of speculative work will be thrown away, causing a lot of wasting power as well. This slide shows the effectiveness of fine-grained clock gating in reducing dynamic power over the coarse-grained clock gating. This graph, the x-axis shows the time, the y-axis shows the number of flops clocked, which is the first-order approximation of the dynamic power. We have this test that has 3 phases, starting from the reset, the high power state, the normal operation as the middle state, followed by the thermal virus, which we tune to exercise as many pieces of the circuitry as possible. With coarse-grained clock gating, after the initial reset period, coarse-grained, the granularity could be at the unit level in this case. There are about 60% of the flop being clocked in the normal operation. The number rises up to 75% of the flop being clocked during the thermal virus. With the fine-grained clock gating, as you can see, during the normal operation, the average is only about just a little bit over 20%. For the thermal virus, the number is just a little bit above 40%. So you can see there's a significant amount of saving to be gained. This slide shows how device-specific VDD reduce the static and dynamic powers. Conventional approach is to supply the same voltage across the whole chip. For the FF part of the chip, actually would burn more power at the same voltage because the leakage is higher. Also, for the FF parts, you can achieve the desirable frequency with a lower voltage. That's how PA Semi approached this problem. We operate at the device-specific optimal VDDs, and we partition into multiple power plane and choose the optimal voltage supply to achieve overall optimal power consumption. Next, I would like to introduce the power-efficient processor family. Power-efficient processor family is a highly integrated design with 3 major components. The first component is the PA60 core. It's a 64-bit power architecture implementation with support for floating point and VMX. VMX is the SIMD instruction extension of the power architecture. This is the core we designed from ground up with 970 performance goal in mind, also with the power budget of 7 watt at 2 gigahertz for the absolute worst case power consumption. The next component is the CONEXIUM Interconnects. It's scalable up to 8 SMP cores, 2 L2 caches, and the 4 64-bit DDR2 with ECC support. The third component is the Envoy I/O system. It integrates SerDes I/O that supports PCI Express, ZAWI, and the SGMII. It also includes offload engines and support miscellaneous I/O such as BOOBus, UART, SMBus, and GPIOs. With these 3 major components, we can design various configurations and target towards different market segments. This slide shows the block diagram of the first product in this processor family, PA60-1682M. On a single die, we have 2 GHz PA60 cores. Has the 1 2 megabyte shared L2 and the 2 64-bit DDR2 memory controllers, and they are all connected using the CONEXIUM Interchange. The I/O section includes offload engine, DMA, bridge that supports 24 LAN SerDes I/O that can support 8 PCI Express, 2 10 gigabit Ethernet ZAWI, and the 4 gigabit Ethernet SGMII. It also includes the debug facility that can monitor the CONEXIUM Interchange as well as the packet bus to ease the design tasks of this highly integrated chip. Now I would like to dive into the details of the PA60 core. The PA60 core implements the IBM power architectures. It also has support for hypervisor and virtualization and implements the power saving mode defined by the architecture. In terms of microarchitecture, it's a 3-way out-of-order superscalar machine. The front end fetch 4 instructions and place them into 64-entry schedule buffer. Out of the schedule buffer, up to 3 instructions can be scheduled out simultaneously and dispatched into the execution engines. The front end uses aggressive yet effective branch predictor to minimize mispredictions. It has 1 load store pipe to support the strong ordering memory model. In terms of bandwidth, the L1 data cache has 32 gigabyte read or write bandwidth. For the L2 has 16 gigabyte read plus 16 gigabyte write. And the DDR2, each of the DDR2 has 16 gigabyte read or write bandwidth. The bus interface between the PA60 core and the CONEXIUM Interchange can support up to 16 transactions in flight. This slide lists the low-power microarchitecture features we put into this core. The front end uses improved branch prediction to minimize the number of mispredictions. We use index-based out-of-order execution engines to minimize the use of power-hungry CAM structure. We also design in the replay prevention mechanism to minimize the number of unnecessary replays. The memory pipeline is designed with hierarchical address translation and a highly integrated memory buffer to minimize the data movement, thus reducing the power consumption. The coherent memory system is designed for high throughput and low latency with the protocol that minimizes the potential write back to the L2 and the memory. We also design in a wide selection of power management capability with the trade-off between entry time, recovery time, and potential power saving. This slide shows the high-level pipeline diagram. The front end takes 3 cycles to decide on the instruction fetch address, then 2 cycles to fetch instruction out of the cache. Then it takes 4 cycles to decode the instruction into microops, rename the register, generate dependency map, and place into the schedule buffer. The scheduler then takes 1 cycle to evaluate the dependency information and pick the instruction ready to be executed and issue them to the execution pipe. The integer and the load store unit read the register immediately and take 1 cycle. The integer operation takes 2 cycles to execute. At the end of the second execution stage, the value is ready to bypass to subsequent use. For the floating point and the VMX instructions, it takes 1 additional cycle to transmit the register index across the core to the register file. Then they take various amount of cycles to execute the instructions. The load store pipe, after the register read, there's a cycle for address generation, 1 cycle for translation, and 2 cycles for data cache accesses. So the load to use latency is 4 cycles. So now we are into more details about the pipeline. The front end is responsible for fetching instruction, decoding instructions, generating dependency map. The center of the front end pipe is the 64 kilobyte two-way set associative instruction cache. The misses in the instruction cache is sent out to the bus. And the next sequential line is prefetch as well. Up to 4 such pending misses can be in flight. After instructions are fetched from instruction cache, they are placed into the instruction buffer. From there, instructions are decoded into microops. And all 4 microops can be renamed in each cycle. Then the dependency map will be generated and placed into the schedule buffer. Branch prediction is a major part of the front end as well. It's very important for effective low-power design. We use various mechanisms to predict different types of branches. Starting with frequently taken branches, we use a 16-entry, 0-cycle bubble next fetch predictor. All the other conditional branches are predicted by a 16K entry, taken not taken, bi-mode predictor. For the target addresses, depending on the type of branches, for the returns, we use a 16-entry return stack. For the indirect branches, we use 64-entry history-assisted target predictor. For the other IP relative branches, we just use the address calculator. We also use the bi-mode predictor to verify the prediction made by the next fetch predictor to minimize the potential misprediction penalty. After branch is issued out of the scheduler, it takes 2 cycles to be executed in one of the integer execution pipe. The heart of the out-of-order execution engine is the scheduler. It has 64-entry schedule buffer, Together with it is a 64 by 64 dependency matrix. The 5 execution pipes and 1 load store pipe are grouped into 3 execution slots. Each slot has a picker. The picker will examine all the instructions and figure out which instruction is ready to be issued. Then 3 instructions can be issued per cycle. After instructions are issued into execution pipe, they could be replayed for reasons such as data cache miss or other buffer full. We design in replay prevention mechanism to minimize such cases. So instruction won't be issued again until the cause of the replay has been resolved. In this way, we minimize the amount of waste of power. PX60 core has 1 load store pipe. The latency to access various levels of caches are listed in this slide. The load store instruction can be issued out of order from the scheduler. The original program order is kept tracked by the 32-entry load store queue. Load store queue is also a centerpiece to support strong ordering. It also supports the bypass from the store instruction to the subsequent load use. After load store misses in the data cache, the miss request is sent out to the bus. And the request is tracked by the miss request buffer called MRB. It can support up to 16 pending transactions. After data gets returned from the bus, it gets filled into the corresponding data buffer of the MRB, waiting for the cycle to be filled into the data cache. After stores get retired, the data is also tracked by the MRB, waiting for the cycle to write into the data cache. For all the stores that write into the same line can continue merging into the same MRB entry until a line gets written into the data cache. The MRB is also responsible for the Snoop evicts as well as regular evict for the fields. So in this way, we have a highly integrated design to minimize the potential data movement, thus reducing a lot of power consumption. Another important piece of the microarchitecture is the address translation pipeline. Power architecture requires 2 levels of translation to be done. First, start with the effective address. You translate into virtual address. Then from virtual address, you translate into the real address. PX60 core uses a structure called ERAD, meaning from that store direct translation from effective address to real address. For the instruction side, for performance reasons, we need 64-entry ERADs. Since programmed execute mostly sequentially, we actually just use a 4-entry micro-ERAD backed up by 64-entry iERAD to satisfy the performance. In this way, only need to power out a very small structure for most of the requests. For the data side, to support satisfactory performance, we do need 128-entry data ERADs. Only when the addresses miss in the ERADs, then they are sent to the memory management pipe to go through 2-level translations. On the 1682M, all the PX60 cores and the I/O section are connected using the CONEXIUM Interchange. The CONEXIUM Interchange implements Moisey-style protocol that minimizes the copybacks to the memory and L2 when the data is modified and requested for shared. In this way, we can minimize the power consumed per reference. The bus runs at half of the core frequency, so the address bandwidth is 1 giga address transactions per second. For the data buses, they are connected like a crossbar. For each data port, it has 2 16-byte wide unidirectional data buses. Another important thing in defining power efficiency is the memory hierarchy. Comparing the on-chip SRAM access with off-chip DRAM access, the on-chip SRAM access saves a lot of power because first, only a few memory cells need to be powered up or need to be clocked. Second, it doesn't need to pay for the I/O power. However, we have to pay attention to the trade-off between the cache size and the power consumption because caches have diminishing performance return with respect to the size. PX60 core implements several power savings modes. The lightest power saving mode is dose. In this mode, the core is idle at a reduced frequency. The power is on, it continues snooping on the bus, so it can recover to normal operation without any state loss. The next power saving mode is nap. In this mode, the core clock is stopped and the voltage is reduced to save power. It stops snooping on the bus. So before we get into the nap mode, we have to flush all the dirty lines from the cache. In addition, during the nap mode, if there's any external snoop to the data cache or TLB, the corresponding structure need to be invalidated. Since the power is on, all the architecture states are retained. The deepest power saving mode is sleep. In this mode, the power is totally off. So before we get into this mode, we have to flush out all the dirty line from the cache. We only retains a few architecture registered, and most of architecture contents ought to be saved to the memory by the software. Upon waking up, the core needs to go through the same reset sequence as the power on reset. So in this way, we have various amount of recovery time with respect to the amount of power saved. Next, I would like to present the projected performance and power number of the first product. The 1682M provides mainstream performance at low power. On a single PA60 core at the 2 gigahertz, it generates greater than 1,000 spec in 2000 and greater than 2,000 spec at P2000. With the 1682M 2 cores, for image processing, it can generate 24 gigaflops for FFT. For system bandwidth sensitive type of application, the sustained block copy bandwidth with 2 cores are 10 gigabytes per second. And the aggregate SerDes I/O bandwidth is 104 gigabit per second. This slide shows the die photo and the high-level partition of the power plants. On a single die, we have more than 15,000 gated clocks. There are separate power rails to the core, the I/O system logic, and I/O pads. We can turn off any I/O whenever it's not used. In addition to the power saving mode we implement for the CPU, the memory controller implementation optimizes the power by having dynamically tuned open page, closed page policies. Even when the core power is down, the L2 and I/O cache still remain coherent because the SRAM power is actually pretty low. All this power management is done by the system control unit located on the bottom right-hand corner. So for the PA60 1682M, with separate VRMs for the PA60 cores and SoCs, the absolute worst case power for the PA60 core at 2 gigahertz is only 7 watts. For the entire 1682M, the absolute worst case power is 25 watts. Summaries. So in this talk, I have presented the work we have done on the power efficient processor family. With a given performance goal in mind, we maximize the performance per watts. With its level of performance and the power consumption, we believe it can enable a wide range of applications across multiple market segments. Thank you very much. I'm happy to take questions.
John Massey. Could you talk some about the micro ops in here? It's slightly unusual to have a lot of that in a RISC chip. Which instructions do you use them for? What's the semantic level difference between those and the
Sure.
instructions? Just sort of you sort of alluded to it, but you didn't say very much.
Most of the power architecture instructions have one-to-one mapping from the power architecture op to the micro ops. But there are a few instructions that does need to be decoded into micro ops, such as low with update or the move string or move multiple instructions.
Tadao Nakamura of COOCHIP's conference series. Your low power design paradigm, that means probably limited to hardware, especially microprocessors only. Because even though you wrote down that software could be for thermal management, I think. Probably you know the transputers by Mr. Ditzer. He described these thermal managements. And I think probably if you think of the very true low power design paradigm, maybe we must think of not only hardware, but also software. Just like today's first keynote entitled.
Yes,
Yes.
Certainly. I think low power design required the hardware to work with software.
Yeah.
So hardware can design all this power saving mode, but software has to be there to take advantage of it. In addition, at the software level, you can change your software algorithm and you can do things in fewer steps rather than consume a whole bunch of power, do a lot of address translation, things like those. There's a lot of work can be done.
Okay, good. Thank you.
Yeah.
Yeah, I have a question on the dye photo. What's the status of the silicon in terms of process technology, speed, availability, and production?
I'm sorry, that's the actual company confidential information, and we're happy to disclose to the customer on the NDA.
You said something in the beginning about Q4, right?
Oh, yeah. In terms of schedule, the chip is ready for sampling in Q4 this year.
Thank you.
Yes.
Mark Semmelmeyer, Juniper Networks. What technique are you using to do the voltage adjustment per part? Are you controlling off-chip regulators, or are you doing on-chip adjustment?
We have on-chip monitor to monitor the process corner of the chip. But in terms of details of how we actually change, that's actually still in the confidential.
Hi. Slide 17, on the instruction scheduler, you have something called replay prevention.
Yes.
I was wondering, you prevent replays from happening by not issuing instruction, or do you starve the instruction pipe from getting any instructions at all?
No, just you only stop issuing of that particular instruction that could be replayed again if the cause of the replay hasn't been resolved. For example, if the data cache miss hasn't come back yet, you stop issuing of that instructions. And because of dependency, all the subsequent instructions will be stopped as well.
So you might end up underutilizing your pipe at the expense of performance.
That's actually a benefit of all the older execution machine. For all the other independent threads, you can continue issuing without any problem.
I mean independent threads as in your multi-threaded processor? Or?
No. This is all the older execution machine with, you could have different dependency inside your single thread program.
Thank you.
Okay, thank you.
Quick announcement for the speakers. Make sure you meet with your session chair before showing up here. So, very good talk, and I'm expecting another good talk coming up. This session chair worked hard. Next, we have Pat Conway from AMD, who has a master's degree from University College Cork in Ireland. He's been at AMD for 5 years as a principal member of the technical staff, and he's now responsible for server architecture. And he's going to describe what my colleague Chuck Moore calls some of the secret sauce on this Opteron generation and future generation, where the NorthBridge part of the chip. Yeah?
Oops. Started not on the first slide. It's all yours. You can use either this. Okay, sure.
Hello, my name is Pat Conway. Today I'm going to be talking about the design of the AMD Opteron processor, and in particular I'm going to be discussing the NorthBridge architecture on the processor. The NorthBridge, briefly, is everything outside of the processor core. So the hypertransport ports, the memory controller, the crossbar. Just a brief recap of the AMD Opteron processor. This is the industry's first native dual-core x86 64-bit microprocessor. It's highly integrated. It has two 64-bit cores with a total of 2 megabytes of on-chip L2 cache. It has a very high bandwidth processor interface with 3 hypertransport ports running 4 gigabytes per second in each direction. So that's a total of 24 gigabytes a second total bandwidth on the interface. And also it has 2 DDR2 memory channels. From a usability and scalability point of view, from its introduction in 2003, we've maintained socket compatibility. So our first part, which was a single core, we're able to swap that out and put in a dual core and realize a significant increase in throughput while keeping the same total dissipated power. So within the same power envelope, we realize the benefits of CMP. And also this part has glueless, supports glueless scaling up to 8 nodes. So that people are building 1, 2, 4, and 8 socket systems with just this component and nothing else, no glue logic. There's no need for external switches or memory controllers, basically because we've integrated the functionality of the switch and the memory controller onto the Opteron processor itself. And also we have support for what we believe is industry-leading system-level power management. Here's the die photo of our Opteron part. It's manufactured in silicon on insulator technology on our fab in Germany. And, and there's the part. When Opteron was introduced in 2003, it really represented a big break with the past. On the left-hand side was kind of the prevalent server blade architecture at that time for x86 blade servers. You had processors sharing a single front-side bus to a chip. This was typically called the NorthBridge, and the I/O hub below it was called the SouthBridge. And the traffic flows from the processor through the memory controller hub down to memory at the bottom. And this is a very long-lived architecture. It's almost 20 years old now. And it has its kind of inherent limitations in that everything, both processors and I/O, share this single point of access to memory, which can become a bottleneck for throughput. And so what you see with this kind of architecture is simply adding more cores up here, extending this on the left here, doesn't necessarily equate into higher performance. So the Opteron processor is quite a radical departure from this architecture. On the right-hand side here, you have 4 Opteron processors, each with 3 hypertransport ports on them. And because you simply have more buses, you have more concurrency, more concurrent data flows in the system. And with the interconnect, it's in open standards, it's hypertransport, it's a high-speed communication standard for low latency, high bandwidth interconnect. And there's an ecosystem with a variety of PCI Express bridges and peripherals which plug directly into the Opteron part. And an inherent advantage of this architecture is that because each chip is a memory controller, there's inherent scaling of memory capacity and inherent scaling of memory bandwidth as you add nodes. So that's a nice scaling attribute. This is a picture of a 4-processor, a 4-socket system. There's 1, 2, 3, 4 large chips here. What's interesting about this photo is what's missing. What's missing is there is no large memory controller chip. because the memory, these are the DIMM slots, connect directly to the processor here. And another thing that's missing is we don't have any memory buffer chips here. So the absence of a memory controller chip and the absence of memory buffer chips translates into lower system level power. Again, this is just another picture of that topology, 4-socket topology. I've just outlined here what I mean by the NorthBridge. The NorthBridge is everything outside. Here are the processor cores. The NorthBridge, it consists of the SRI, the system request interface, the crossbar, the memory controller, and the hypertransport bus. So as you can see, these two processors are interconnected with a high-speed hypertransport link, 4 gigabytes per second per direction. And also, we have I/O connecting via hypertransport, a non-coherent hypertransport here. And the memory interface then to DDR2 is 12.8 gigabytes per second per chip. So that's a total of 52 gigabytes a second. Just some detail on the NorthBridge internal microarchitecture. This shows a simplified view of the NorthBridge. Basically, the processor cores, you have their system request queue, you have the crossbar in the center of the chip, and we have a memory controller and DRAM controller on the chip as well, and also the hypertransport ports down here. So the main traffic flows through this chip are, you start out with an L2 MIS, a memory access, which allocates an entry in their system request queue. That then is routed by the crossbar to the local memory controller, if it happens to be a local memory access. If it happens to be a remote access, that same request follows this flow through the crossbar, out hypertransport, and then in hypertransport on the home node to the memory controller. And this fabric here supports 4 virtual channels. That's needed to be able to build deadlock-free servers. The 4 channels are requests, posted requests, probes, and responses. In the next 2 slides, I'll be talking about the flow of commands and the flow of data in the crossbar. So this is how the flow of commands are handled in the Opteron NorthBridge. Architecturally, it's a very simple design. The crossbar is a very simple design. It's a single level mux with 5 ports, 1 port for the processors, 1 port for each of the 3 hypertransport links, and a port for the memory controller. And the first point is that this is a full custom design, and it clocks at the same rate as the CPU core. So our processors run at up to 3 gigahertz now. So this multiplexer is running at a rate of 3 gigahertz, and it can route 1 8-byte command address packet to the output on each clock. So there's a very high service rate at the output port here of the command multiplexer. So, and the buffer sizes are as shown. One thing I'd like to point out here is each port here has a pool of buffers for commands, and these commands have to be allocated. There has to be an allocation of commands to the different virtual channels. We have 4 virtual channels, and I'll be discussing the allocation of buffers to virtual channels in a minute. I'll get back to this. This is the data flow in the NorthBridge. The flow of data, first of all, data is transferred on cache line size quantities. So on Opteron, the cache line is 64 bytes. And so we basically, in this scheme, we have a 2-level crossbar, 2 levels of muxing, basically. Again, it's clocking at the same rate as the CPU core, so a very high switching rate, which is quite different from an ASIC implementation of a crossbar where you typically have more multiplexers. Here we have few multiplexers, but switching at an extremely high data rate. And we support cut-through routing. So when the first 8 bytes of a cache line is received at a hypertransport, that is routed immediately to the output port, its destination, and we can support concurrent transfers from different input ports to different output ports on a clock-by-clock basis. And this helps minimize the latency to that critical word of a memory access. And so there are a total of 5 ports, the 3 hypertransport ports here, and there are 2 ports here, one from the processor cores and one from the memory controller. This is, you know, anytime you develop a new architecture, you always come away from it having learned a few lessons. We have several years of experience now working with Opteron and working with different size systems. And one unexpected issue that kind of surfaced was this question of allocating buffers to virtual channels. Our coherence protocol is fairly involved, and this shows an example of a single Opteron read transaction originating on node P3 going to node P0. And all of the arrows here correspond to messages which need to be delivered in order to complete this transaction. So it starts out with a read transaction from P3 to P2 going to P0. P0 is the home node. It reads memory. It also delivers probes to itself and to the other nodes to which it's connected. And finally, every node then returns a probe response back to the source node, indicating what the sharing status of that line is. And as you can see here, this is a 4-node system. A naive allocation of buffers to virtual channels, say in equal weighting of buffers to virtual channels, that is not the right answer. The best allocation is allocating, if you count the number of messages on the different virtual channels here, it turns out that only 2 messages on the request channel, 3 on the probe channel, but 8 on the response channel. So it's a very asymmetric kind of allocation that gives you the best performance. And this issue is especially pronounced on our 8-socket topologies because they are quite asymmetric. Another lesson, I think, key lesson that we took away from our experience with Opteron is that memory latency is the key. It's vital to application performance. And this is something that I think we got right on Opteron. On the x-axis here, I show different topologies starting with 1 node, 2 nodes, 4-node square topology, and an 8-node twisted ladder, and an 8-node ladder topology. Well, the first point to make is our latency, the latency in our 4-node topology, you have different classes of latency because it's a distributed shared memory architecture. Some memory is near, so if I'm accessing memory on the local node, I get a certain latency, whereas if I'm accessing memory on the remote node, there's a higher latency. But the point I'd like to point out is even our 2-hop latency is better than can be achieved with an external memory controller. External memory controllers typically run at a lower frequency, and they also have layers of buffering between the controller and DRAM. And so our worst case latency is better than can be achieved with the off-chip memory controller. But this is kind of a zoom in showing the kind of scaling that we get on different applications going from 1 socket up to 8 sockets. The good news is we do see positive scaling, 1 to 2 to 4 to 8. You might wonder, what is this? There are different applications here. There are 2 flavors of TPCC, Spec Web, Spec SSL, and Spec JBP. What's the primary factor accounting for the difference in throughput on these applications? And not too surprisingly, it's cache miss rates. So those applications which have the highest miss rates cause the most traffic on the interconnect and obviously are most sensitive to memory latency. Whereas on the other hand, something like SpecJBB, which is a very small code and data footprint, runs well out of its cache, and so you see very good scaling with node count. And so then if you take, for example, this number and divide by the number of sockets, then that gives you the performance of a processor in that topology. The only variable here is the topology, is the memory latency that this processor sees in the fabric. So this is the kind of sensitivity that we get as we go from a topology where all memory is local to a topology where half of the memory is local and half is remote. This is the 4-node, 8-node. So obviously, you would like the processor always to be operating in a configuration where the latency, the diameter of the network is relatively low. So diameter is the distance between the maximum distance between any two nodes in a system. So you'd always like to have topologies which optimize the diameter. And so looking forward, there's some important lessons from that to be taken forward, and which we have incorporated into our next generation processor architecture. So now I'd like to talk briefly about our plans for our next generation processor architecture and what you can expect to see in the years ahead from AMD. One interesting development has been the emergence of hypertransport-based accelerators. Hypertransport is a very low latency, high bandwidth interconnect standard. It's an open standard available to anybody. And the idea here is to open up the system, our Opteron platform, to the system developers so that they can provide differentiation for focused application areas. Examples of accelerators that could be developed to take advantage of this would be media accelerators, floating point accelerators, service-oriented architecture, and so on. And so the concept here is you have your Opteron platform, and you have these non-coherent hypertransport ports, which can be connected. You can connect directly your accelerator to them. Because the alternative, if you're a system developer, the only alternative way to connect into a system is through the PCI bridge. So what you save basically is you avoid going over this PCI Express bridge. And so the intent here, this is a program called Terenza, and this is something that we'd like to encourage people to design accelerators directly onto hypertransport. So they could be coherent-based or non-coherent-based. You can have homogeneous or heterogeneous computing model. It really is kind of like a sandbox for system developers. And we are planning architectural enhancements for fine-grained parallel communication and synchronization to enable this and to make it perform well. AMD's next generation processor looks like this. This is a part that we have taped out. This is a die plot. It's a native quad-core die. There are 4 die. It has an expandable shared L3 cache, and it's manufactured on 65 nanometer silicon on insulator technology. We have an enhanced direct connect architecture, so we've completely overhauled the NorthBridge. We now have 4 hypertransport ports, and each hypertransport port runs at a rate which is 2.5 times faster than what we have today. So it's hypertransport 3. So instead of being 4 gigabytes, it's 10 gigabytes per second in each direction. We have an enhanced crossbar. We have support for next generation memory, DDR3. The architecture supports FBDIMM when our customers require that. And we've enhanced our power management and RAS. I'll get a little bit into our power management enhancements in a minute. And we've also enhanced our cores as well. We've 32-byte instruction fetch. We have an improved branch predictor, out-of-order load execution for double precision floating point operations per cycle, dual 128-bit streaming stores, and some new instructions as well, as listed here. Another key architecture enhancement is our new cache structure. We've gone from a 2-level cache hierarchy to a 3-level cache hierarchy. So we believe that through more efficient memory handling, we can reduce the need for brute force cache sizes. Our latency to memory is lower to begin with. It was very aggressive to begin with. So that right there mitigates the need or the pressure to add huge caches on the die. What we have is we have a dedicated L1 cache, instruction cache, and data cache in each core. This is the locality keeps the most critical data in this cache. And this has the lowest latency, of course, and it supports 2 120-bit loads per clock. We have a dedicated L2 cache, 512 kilobytes, which is sized to support the majority of working sets today. And it's dedicated to avoid conflicts, which are common in shared caches. And finally, we have a new level 3 cache. And this has a highly optimized allocation policy, which optimizes the movement, placement, and replication of data for multi-core, and it's ready for expansion. Initially, it will be 2 megabytes, but it's designed to be highly scalable. Another, I think, really exciting development from a server architecture perspective is we've added additional hypertransport ports. The fact is the shortest distance between any 2 points is a direct path. And by adding additional hypertransport ports, we can provide that direct path to system builders. So what we've done is we support 2. Opteron today has 3 hypertransport ports. We've added a 4th, so 4 16-bit hypertransport links. Or through a configuration, we can make each of these 16-bit ports an 8-bit, 2 8-bit ports, independent 8-bit ports. And what this enables is it enables building fully connected 4-socket and 8-socket topologies. And this is a really huge bonus, I think, in an improvement going forward. It gives lower latency because you have a direct connection between any pair of nodes. You have higher bandwidth, and I'll be giving some numbers on that. And the benefits, in a nutshell, are lower latency, higher bandwidth, lower queuing delays, lower latency under load. So all of this is goodness. And it's attributable to additional hypertransport ports. So to illustrate what I'm talking about here, this is a 4-socket system that you would build. This is how you would build a 4-node Opteron today. It's running at 2 gigatrans per second, which is hypertransport 2. It has a diameter of 2. So the maximum distance between any node, say P0 and P3 is 1 hop, 2. It's 2 hop diameter. And this term diameter is kind of a synonym for latency in a way. The latency of this system, the average diameter would be, for example, here, P0 accessing its own memory has 0 hops to memory. P0 accessing P1 or P2 is 1 hop to memory, and P0 accessing P3 is 2 hops to memory. So if you take the average of that, then the average number is 1 hop to memory. And what we see running a whole lot of server workloads is that this is, in fact, very representative of how memory is accessed in a running system. Usually the distribution of memory accesses is uniformly distributed. So to within almost a small fraction of a percent, it's very typical for 1/4 of the accesses to be local, 1/4 here, 1/4 here, 1/4 here. So this is a kind of a typical operating scenario that we have. And so the metric for latency is diameter, average diameter, and the metric for bandwidth is something that we call crossfire bandwidth. This is a metric that we like because what it is it's the link-limited bandwidth. If each processor were accessing its own memory and that of every other node in a kind of a uniform fashion, and if you had infinite buffers and if there were no other constraints in the system, then this is the bandwidth that you could see in this topology. So it's 14.9 gigabytes a second divided among the 4 processors. So that gives you about 3.3 gigabytes per second per node, actually, per node. Now, so the benefit, my point here is that going from this topology, by adding one additional hypertransport link, we can go from this topology to this topology, where we've basically added 2 additional links. And that provides you with a fully connected topology. And simply that one change, still running at the same frequency hypertransport, that reduces the diameter to 0.75, because now you don't have a 2-hop case, you have 3 1-hop cases. And the crossfire bandwidth, this bandwidth metric here, doubles, which is a little surprising. But the reason for that is any packet, in this scenario, a data packet might have to visit this link and this link, whereas in this scenario, you never visit more than one link. Any packet going from point A to point B will only visit one link. And finally, going from hypertransport, which is 2 gigatransfers per second, to hypertransport 3, which here I'm showing 4.4 gigatransfers per second, that gives you a doubling again. So the crossfire bandwidth goes up by a factor of 4. So this is good on 2 counts. You have a lower latency and you have a higher bandwidth. And the picture, okay. And the picture for 8 nodes is even more dramatic. This is the best you can do today. This is a topology where you build up an 8-node using 2 fully connected 4 nodes, and this is a fully connected 8-way. Go up a factor of 6 higher. And quickly, I'd like to just, why are we going to quad core? That's probably the single biggest change we're planning. Basically, the reason has to do with the relationship between frequency and power. Frequency and power have a nonlinear relationship. A small increase in frequency gives a large increase in power, and a relatively smaller increase in a linear increase in performance. A decrease in frequency has a nonlinear effect on power, it halves it, and a smaller effect on performance. So that phenomenon allows us, within the same power envelope, to have higher throughput. And the reason is this power versus frequency is nonlinear, whereas performance versus frequency is linear. Clocks and power planes, we've added clock domain for each core. We've added a clock domain for the NorthBridge. And this allows us to support what we call DICE, Dynamic Independent Core Engagement, where we can run the cores in a variety of modes. So this is where all cores are running at maximum throughput. This is a 60% power state, and this is lower still, 45% power state. And so here's my last slide. This number is not the national debt of the United States. If you ever go to Times Square, you'll see a billboard where they do have the national debt displayed. AMD, in order to heighten awareness of how important managing power is in data centers, we basically erected a billboard in Times Square which displays the amount of money which will be saved worldwide in data centers if Opteron processors had been used. Thank you.
Sean Massey again. Two questions. One on the performance charts you had. In the interest of full disclosure, were those NUMA-aware OSs in that memory allocation, or were they interleaved?
It was a mixture. Some were NUMA and some were running. NUMA is where you map all the memory in kind of contiguous ranges, whereas interleaved is where you interleave on a page basis. These were a mixture of the two.
Okay. The second question is, when you were talking about the allocation of buffers and so forth going back, can you talk just a little bit about what goes on when a processor does a synchronization instruction? We had some tutorial stuff yesterday on programming with such things. I mean, it looked like there are a lot of messages that are going to be flying around if you do a test and set or the moral equivalent thereof. Did you guys do anything special to help those sorts of things for parallel programming?
Well, in our next generation, we are planning to put in special support for migratory movement of locks. So that would be one example.
So on slide 25, you had to kind of rush past that really quickly, but you showed two voltage planes, one for the cores and one for the NorthBridge.
That's correct.
But the L3 cache isn't shown there. Which plane is that on?
The NorthBridge.
Okay. And does it share the same PLL?
Yes, it does.
Okay, thank you.
You had mentioned a note about supporting accelerators for for fine-grained parallelism. So how is that accelerator that connects through the hypertransport compared, for example, to a function that is actually integrated on a system on a chip? I mean, not in case of AMD, but relatively.
How efficient is our synchronization?
Yeah, I mean, latency and throughput through this hypertransport, as opposed to another implementation that puts that piece of accelerator on the system on the chip.
Well, that's a good question. I think probably if you had an integrated solution, you'd probably do better. But I was really trying to contrast what's possible with PCI Express versus what's possible with hypertransport. So the fact that you have lower latencies with hypertransport accelerators speeds up this, the synchronization.